So we were discussing the concept of making an inverted index, right? So an inverted index, as we have discussed, will be basically consisting of two parts, a dictionary and a postings. So basically making an inverted index consists of storing two things. One, dictionary, which is basically a list containing all the terms in the vocabulary, and a posting list, which is basically, you can consider a linked list for each term in this dictionary. So for each term in this dictionary, there will be a pointer, which is basically the pointer to the posting list or the start of the linked list, which is containing the document IDs in which these individual terms are basically occurring. Now, our goal, again, just to give you a recap, was to allow searching of a term in the dictionary as quickly as possible. This is important. So all these things we are doing with the hope to reduce the search time, because as we have discussed, considering a Google search, if the Google is returning us a very good result after 5 minutes, it's not actually acceptable. We want the result quickly. So all these things we are doing to overcome or to reduce the execution time or to reduce the retrieval time. Earlier we started with a simple linear search where we are using grep, but we are here trying to develop something better than that. So with the hope of that, we have discussed on creation of this inverted index containing dictionary and postings. Now this dictionary, along with the actual term, it can also contain the document frequency. That is, the number of times this term is actually occurring in the number of the number of documents that this term is basically containing in. So in this case, this Brutus term is basically present in these 8 documents. These are basically the doc IDs as we have discussed. So Brutus is present in these 8 documents. That's why its document frequency is basically 8. For Caesar, the document frequency is 4. For 8, and for Calpurnia it is 4. And the third information that we should be storing in the dictionary is basically a pointer to the start of this posting lists. Now these 3 items should be stored for all terms basically in the vocabulary, right? All right, so this was the entire process from the raw data. This is the raw data to the creation of basically the entire posting lists or the entire dictionary. This is basically the dictionary. So in the creation, in the process of this creation, we have encountered some steps which requires more thorough discussion. So what is this? So basically, given 2 documents, doc 1 and doc 2, the first phase is basically tokenization and stopword removal, and in general, as we have stated the thing like doing the linguistic preprocessing. This is basically doing that. So all the words are basically downcased, right? Julius J small, Caesar C small, and so on. Along with, there can be some stopword removal as well, but in this example, I have kept the stopwords. Now, from this set of tokens, which is basically a pair containing the term T and the DID or doc ID in which it is actually occurring, the term is actually occurring, it will be containing. So if there are, say, 100 terms in the vocabulary, in the entire vocabulary, then in this list, there will be 100 items. Note that this 100 items, there can be repetition, like as we have seen, Caesar is present in document 1 as well as Caesar is present in document 2, right? So this is basically, there can be repetition in this list. Now the next step is to combine or to sort them together such that the same documents, such that we can get the list, basically the posting list of each of the terms, right? So basically, given a term, what we need is, we want to actually, at the end of the day, we want to get a list of doc IDs in which this term is occurring in. Now in this list, this term T is basically present at multiple position. There is no way, we need to combine this multiple occurrence of these multiple T's to get this posting list. So to do that, as we have said, we will be basically performing a sorting here, which is basically the important step that we want to focus a little bit. So given this, our target is to sort this based on the terms or based on the lexicographic order, that is a dictionary order, A, B, C up to Z, and then based on the doc ID. So as you can see, Brutus is present in doc ID 1, doc ID 2. Caesar is present in doc ID 1 and twice in doc ID 2. So they are basically sorted. So if I consider only this part, so Caesar has been sorted. Earlier, the first presence of Caesar was here, and the second place of occurrence of Caesar was here, and the third was here. So at the end of the day, after this sorting, we are basically ending up with all the Caesars together here. And from this, we know that basically what we can do is, we can make a node like Caesar, which will be basically the term in the dictionary, along with the posting list, which will be containing 1 and 2, which is basically the doc ID in which this term, which is Caesar, is actually occurring in, right? Now there is one issue with this kind of a sorting. Now all the sorting algorithms we have looked at during our limited exploration of computation, we have seen like quicksort, merge sort, and some sorting algorithms in Python. For all of them to work, the data that we want to sort should be in which memory? Can someone say? So as I said, in the last class, there are two primary types of memories. One is primary memory, which is RAM, and secondary memory, which is basically the hard disk. So to make a list, to sort a list, where this list should be residing, whether it is in RAM or in hard disk. Anyone?
RAM.
Correct. So it should be in RAM. But we know the capacity of RAM is limited. Now consider this list is too large. It might be the case that RAM will be overflown, or there will be not enough space to store all these entries. Okay, so this list can only be sorted until and unless we are ending up with all these tokens. Like if there are, say, n number of documents, all of them will be processed like tokenized and linguistic processing applied. If there are, say, n documents, after this tokenization and linguistic preprocessing, until and unless we are getting the entire list of all the terms and their doc ID, this thing, we will not be able to perform this sorting, right? So now let's consider this from the programming point of view or the memory point of view, memory consumption point of view. Now, with our limited knowledge of C, we know that the size of a character is basically from 1 byte to 4 bytes. Sorry. So if it is ASCII, if it is storing an ASCII, if I simply declare a C character like char C, it is basically an ASCII character which will be taking 1 byte. There can be another type of character in C which is called wide character or wchar underscore t. So this type of a character can actually store non-English or any Unicode values as well. This is called wildcard character. Not wildcard, it is basically wide or wildcard character, not wild. So this would be taking, based on the operating system, it can actually take 4 bytes of space, right? And this would be taking 1 byte, sorry. Now, considering the maximum length of a term in the vocabulary having say 20 characters, the length of the term would be 20 bytes, maybe, if we are only considering ASCII. And it can also be 80 bytes if we are considering Unicode, right? Again, I'm repeating, if the length of the highest, if the highest length of a term in the vocabulary is having 20 characters, then each character is taking, in case of an ASCII, it is taking 1 byte. So to store the term, we need 20 bytes. In case it is Unicode character, then we need 80 bytes, 4 bytes per basically per character, and 20 characters are there. So in total, 80 bytes. So we need per character per term 20 to 80 bytes of memory. Now the second thing is basically the doc ID, which is basically an integer. So for this integer, we know based on the operating system that we are using, the size of int can be either 2 bytes or 4 bytes. Or if we are using a long integer, it can be more than that as well. Which is basically here, this int is basically this doc ID. So size of doc ID will be again 4 bytes or 8 bytes. So now the space needed per token here is basically, for the term, it would be taking 20 bytes to 80 bytes of space. For storing the doc ID, it would be taking either 2 to 4 bytes of space. Together with that, if we are storing the frequency as well, like the collection, the document frequency that we have discussed, it would be again, it would be an integer, it would be taking some space nearing about 2 bytes or 4 bytes based on the operating system. So if we consider only this ASCII and this, if we do the maths, we are ending up with 24 bytes per entry here, right? And if we are considering ASCII, Unicode, it is actually taking 88 bytes of character, or 88 bytes of space in the memory per entry in this list. Now, for a relatively small collection such as RCV1, RCV1 is a very small collection which is containing around 800,000 documents. Although from the number it seems quite large, but it's not actually that much large. The size of this RCV1 dataset is basically 1 GB, around 1 GB, right? For a collection like this, which is considered as a small collection, it actually contains around 100 million tokens. So there will be 100 million rows here, right? And for each of these 100 million rows, how many space we need? Either 24 here or 88 here. As this RCV1 is basically a test collection containing the news article published in Reuters. So this is basically English. So in that case, we need 24 bytes of space, right? As it is simple English, in English we can actually use ASCII to represent it. So basically, now considering this, can you say how many space it would be needed to store this thing in the primary memory? So if we do the math, it is basically 100 million. So basically there will be this many zeros, if I am not mistaken, into 24. And if we do the math, it will be 2.4 GB. 2.4 gigabytes of space will be needed to store this list in the memory. Note that this is a relatively small collection. For a small collection, we need 2.4 GB of space in the primary memory to sort. Now we know after sorting, while sorting, it actually will be considering some auxiliary spaces as well, right? So it would be essentially to sort this list, it would be taking more than 2.4 GB of space. Now, as we have discussed in the last class, considering the running operating system as well as the running programs, it might be the case that we will be running, running sort of memory if we are taking, if we need this much of memory while running this kind of an operation. Now, can we do something better than this? So one alternative is, or one way of optimizing this is, instead of using the term itself, we can use the term ID, which can be an integer or a long int, which is long enough to contain the term itself, right? So basically the long enough to cover all the terms in the dictionary or in the vocabulary, right? How this will be useful? So basically, what we will be doing is, we will be, let's say, similar to the doc IDs associated with the actual document. If we use some TID with the actual terms, so we can start with 0 with the term say A, 1 with say AA, 2 with say term N, and so on and so forth, right? And if we are ending up, so basically, so using this, earlier we were storing this, right? We are storing this. Now, if we store this TIDs, which will be basically integer or long integer, it will be a little bit of space saving, but still it will be too much space consuming. Now, the main problem was to sort the posting list in the memory, right? So while indexing, basically if we again look at the scenario. So while indexing, documents are parsed one by one after the other. All the documents will be parsed. Let's say the collection is containing say 100,000 documents. So we need to basically parse them to get the token. That is, we need to tokenize them. So for each document, say if it is document 1, document 2, we need the T1, 1, T2, 1, this kind of a pair for all the terms in in document 1, then similarly for document 2. Then after traversing the entire collection of say n documents corresponding to and the corresponding term lists, we will be able to perform the sorting. But again, the question is, can we keep all the postings in memory and do the sort in memory? The answer is not at all. Even for a small collection like RCB1, we have seen that it would take 2.4 GB of space. And considering a large collection, we will be discussing some large collection of, say, some of them, the names are, say, WT10G, which is containing the size of which is actually 10 GB. We will also be considering another collection called Gov2, which is containing the size of which is around 430 GB. And we will also be discussing about another collection which is a very popular one called ClueWeb. There are two versions. In 2009, one is proposed and another is in 2012. The ClueWeb 2009, the size of it is actually 5 terabyte. So considering this kind of a collection, we know that 1 GB of collection, which is the RCB1, is actually too tiny actually. All right. So the common issue is basically exhaustion of primary memory. So we need, at some point, we need the intervention of secondary memory. That is, we will be storing certain part in the external disk, that is HDD or hard disk, and we will be performing the sorting in the external disk.